Hello everybody, welcome to physics. Today we're still talking about energy, and we did our little lab yesterday, right? And what we did was we took the Hooke's law apparatus, and you had your spring here, and you had a platform, and you kept putting mass on here, and that mass applied a force to the spring, and in return the force, or the spring, had to apply a force to the mass. Do you guys agree with that? Okay, so what happened is, let's say that this was equilibrium, okay, which means, in Newton's laws, when we say equilibrium, it means there's a net force of 0 on the object, okay? So we know that gravity is pulling down on this, right, but the spring is also pulling up on it, so it just sits there. There's no acceleration, there's no velocity, so it just sits there. That's what equilibrium is. And then as you put mass on, you got a stretch further and further from equilibrium, right? And as we went further and further down from equilibrium, like if you take the mass off and put your hand on, and you take this spring and you pull it down, what happens as you get further and further down? Gets harder and harder and harder, correct? Okay, now the springs that we deal with in physics have some space in them, which means you can stretch them that way, you can push them or compress them that way. So you can imagine if you're going to push on this, it's going to get harder and harder and harder as you get further away from equilibrium. Do you agree with that? Okay? So when we talk about pushing on this spring, how does that fit into energy and work and stuff like that? Any ideas? Well, what is the definition of work? Okay, mathematically we can say that work is equal to a force that's parallel to a displacement, right? And work is the ability to give something energy or to change energy, right? And energy is the ability to do work. So it's kind of hard to define these things without each other. So we have to talk extensively about it. So let's talk about the force here. Okay, so yesterday, well, before we talk about that, yesterday I asked you to talk about the relationship between the force of the spring and the displacement from equilibrium, right? And you got this graph that looked like this. And that slope is constant, which means what about the relationship? Well, this is linear, yep, and that's what we get out of a constant slope. That's kind of the definition of a constant slope. Okay, so force is directly related to, oops, that didn't quite work out. That's a bad alpha. It's directly related to displacements, right? And what that means is as one goes up, the other goes up. Okay, and it's linear, so we know that there's going to be a slope value. So the slope of this graph is going to be newtons per meter. Do you agree with that? Okay, so and then if we think about what we were talking about earlier, as we got further and further and further from equilibrium, which on the graph would be in this direction, the force of the spring got bigger and bigger and bigger. And since this is linear, that means that change is constant. So if we have a constant slope, we have a constant change in this relationship here. Okay? Do you agree with that? So, in other words, my newtons per meter for that spring is constant. Right? Okay? Now, if we look at so let's say I have this spring here, and then let's say I have this spring, Oh, that didn't work. Well, let's say I have a really thick spring. Okay. Which one do you think is going to have more force associated with its displacement from equilibrium? One or two? Two, right? Because it's more metal, it's got a heavier spring. So, you know, they can get really, really thick and then they put them in cars, right? So, how does that fit into this scenario of this constant thing? Do you think that would change? How would this change from 1 to 2? What could we say about the constant from 1 to 2? Right, so there'd be an increase in the constant, which does that what number does that pertain to? The top number or the bottom number? The numerator. So you get more force for every distance or displacement that you take the spring from equilibrium. Does that make sense? So what we do then is we say that we have K. A K. And that's what we name our constant. Okay? So if you look at a formula that has the force of a spring in it, okay, the force of a spring, here's our formula, is negative kx. And so if you would solve for k, you would see that it's force divided by displacement, which is what we've been talking about. Do you agree? So, simple terms. What is the K? It's a way to what? So the K is an identifier of how strong the spring is, or a rating for how strong the spring is. So the bigger the K we have for a spring, the stronger the spring is. Because with the same displacement, so if we keep our displacement from equilibrium constant, and we increase our K, you can see with this formula that the force of the spring becomes bigger. Now, how did they come up with a K? Well, I'll tell you how. They did what you guys did with many different springs. And they saw that these constants are, well, first of all, they're regular. There's a regular slope. And second of all, they are dependent upon the strength of the spring. So this is called Hooke's law. Hooke's law is the force of the spring is negative kx. And this is for ideal springs, which means for every displacement you do, it's going to be the same relationship between force and displacement. Now, yesterday we weren't using ideal springs. That's why I said start with 100 and end somewhere around 325, because I knew after that things, well, first of all, 325 would get too far to measure. But I know before 100 it's not quite constant, because there's, you know, intermolecular forces and there's other things that happen that cause a spring to be springy. But those were actually pretty good springs. They were nearly ideal in that range that we tested them. If I would have pulled it too far, the spring would never come back. It's because I disrupted the intermolecular bonding, the metal pieces, and the sheets of metal started to slide across each other. Okay, so let's look at how this works. Well, first of all, force equals negative kx. Force is a vector, right? Why is it negative kx, then? Because x is the displacement, right? So here's my spring. If I move the spring downwards, my displacement is in the negative x direction. Okay, the spring, once I get down here, the spring is going to want to pull me back up. Do you agree? What direction is that force in? The opposite direction. And so that's why this negative sign comes into play, because the force of the spring is opposite of the displacement. Now, vice versa, if this is equilibrium and I push into the spring, when it gets compact, I've displaced in a positive x direction, but the force of the spring is going to push me backwards, which is opposite direction. So there's your sign convention on that. Okay, so if we look at work, okay, so work equals force parallel displacement, and really it's an average force. Do you agree? So let's take a look at what happens Well, actually, you already did. You got a force here and a displacement here. You saw in lab that this is your relationship. Do you agree? Okay, so if I'm trying to figure out how much work a spring can do, and I'll just go like this and I'll say that I'm going to move this spring down by a displacement of x, being this x right here. Okay, then I have to look at that, because this is the only, I get one measurement when I compress or stretch a spring, and that's how far it's displaced. Okay, so right here, force here then is going to be equal to negative kx. Because of our Hooke's law, because of the lab that you did, and now you see the formula, force equals negative kx, that's going to be the force that the spring puts on at that point. Now, if I release the spring, does this force change? And how does it change? Equilibrium. So, everybody's right here. What you said is when you pulled down on this spring, you said that, hey, I'm giving the spring a potential energy. I'm giving it an ability to do work. So when I release the spring, what's going to happen to the spring? The spring is going to go back towards equilibrium, and if there's something on the spring, it's going to force on that, and it's going to work on that item. Now, in this case, if this is, maybe this is inside a dart gun, and I've got my spring down here, an X. When I release that, the spring forces up over this displacement. Do you agree? And then after that, the spring might pop out a little bit, but due to Newton's first law, Energizer Bunny, lazy, or couch potato law, that spring is gonna become disconnected from the dart, because the dart continues on its velocity because there's no force on it stopping it, but the spring starts having a force back on itself to keep it back, so it might bounce up and down. So right at this place here, the spring is done working on the object that it was touching because it releases it due to Newton's first law. Okay, but it worked on it. So we got to talk about the work that the spring did. And we know work is average force per distance. We know that the spring maxes out at kx. But how, then, is the question, how is the delta force occurring over this spring going back to equilibrium? Well, at equilibrium is right here. What's the force at equilibrium? It's 0. Right? The force at equilibrium is 0. And how does that change happen? Well, it gets less and less and less and less at a regular rate if it's an ideal spring. Do you agree? So the average force then becomes force max, which is up here. This is the force max of the spring, plus force minimum. Okay, I'm going to erase this just for now. And then you divide it by 2, right? You take an average. As long as it's a linear average, you can just divide it by 2. Or a linear situation, you can divide it by 2, right? So if this is 0, then it becomes force max divided by 2 is the average force. How much distance or displacement does that spring force on that? For an x, right? In this case, and this would be the x right here, from here to here. So if we take this a little bit further, we say the work that a spring can do is equal to the potential energy that's wrapped up in the position of the spring away from equilibrium, is equal to average force times displacement, that's parallel. Our average force then is 1/2 of the max, right, times the displacement. Okay, so our potential of the spring is 1/2 Okay, now we have to, with variables, define our max. Oh, look, it's negative kx. 1/2, I'm going to leave the negative out of there because this is energy stuff, kx, and it does that force over what distance? X. So we get our new formula. The energy of a spring then is 1/2 kx squared. Okay? So that's our potential energy of a spring formula. Does it make sense how we got it? Okay. Thanks to you guys doing the lab, because I was wondering if that was the real situation or not. And let's also look at this graphically then. So I'm going to erase the rest of this stuff here for a second. Some of this stuff anyway. See if it pops back. Oh, I guess I was lying. I didn't erase it for a second. It was more permanent than that. Although, realistically, it's probably in the computer somewhere, right? Okay. So, graphically, work equals force times parallel displacement. Okay? So if I take force distance graph, okay, let's say that I force on something with 10 newtons of force over 10 meters. So there's 10 and 10. What would that graph look like? It's a constant force, right? For 10 meters. Okay. So remember we talked about how the area of a graph means something. So if you look like this area of the graph means something. And the area is force times distance. So this, just like area, is base times height. This area is force times distance, which gives us work. Okay. And so if you look at this graph here, the area under the curve means something. Well, it's still force times displacement or distance. But this time it's only 1/2, right? Because that's how you get the area of a triangle. Is you have your 1/2 base times height. So you should be able to see that this is work as well, graphically. Okay. So now we have to answer the question, how does all this work? So, I'll give you a couple sample problems on the next video.